A single experiment once proved that light could behave as both a wave and a particle, and that discovery shattered 200 years of classical physics. That moment didn't just tweak science, it forced humanity to rebuild its entire playbook for understanding the universe. The origins: when classical physics failed. For centuries, Newtonian mechanics delivered a stable, predictable framework for explaining motion, forces, and gravity. By the late 1800s, scientists believed the universe was nearly solved, with only a few small mysteries left. But those small anomalies, like blackbody radiation, the photoelectric effect, and the structure of atoms, turned out to be cracks that would eventually break the entire foundation of classical physics. One of the earliest disruptions appeared in the study of thermal radiation. Experimental data simply didn't match the predictions of classical physics. The mismatch was so severe that it became known as the ultraviolet catastrophe. This crisis signaled that something fundamental was missing, setting the stage for a scientific revolution. Max Planck and the birth of the quantum idea. In 1900, Max Planck delivered a radical fix. He proposed that energy is not emitted continuously but in discrete packets, or quanta. This was not a philosophical statement, it was a mathematical necessity to match real-world experimental data. Planck's constant, a tiny numerical value, quietly became one of the most important constants in all of modern physics. Although Planck himself did not fully embrace the radical implications of his theory, the door was now open for a new kind of physics, one in which nature behaved in discontinuous, probabilistic ways. Einstein pushes the boundaries further. In 1905, Albert Einstein expanded Planck's quantum idea by explaining the photoelectric effect. He argued that light itself comes in packets called photons. This was a direct challenge to the long-held belief that light was purely a wave. Einstein's work earned him the Nobel Prize and established quantum theory as an essential framework for describing the microscopic world. His insights also laid the foundation for technologies like solar panels, lasers, and modern communication systems. Bohr and the first quantum model of the atom. Early atomic models struggled to explain why electrons didn't collapse into the nucleus. Niels Bohr stepped in with a breakthrough. Electrons occupy discrete orbits and can jump between them by absorbing or releasing quanta of energy. The Bohr model wasn't perfect, but it proved that classical mechanics could not describe atomic behavior. This realization accelerated the movement toward a fully quantum description of matter. Heisenberg, Schrödinger, and the rise of quantum mechanics. The mid-1920s saw the explosive development of quantum mechanics as a complete theoretical framework. Werner Heisenberg pioneered matrix mechanics, focusing on observable quantities and their relationships. His uncertainty principle, stating that position and momentum cannot both be precisely known, challenged the classical belief in complete determinism. Erwin Schrödinger introduced wave mechanics, which explained particles as wave-like entities governed by his now famous equation. Though conceptually different, his approach was mathematically equivalent to Heisenberg's, unifying the quantum theory under a consistent structure. Dirac, Pauli, and the deep structure of matter. Paul Dirac pushed quantum mechanics into the relativistic domain, predicting antimatter long before it was observed. Wolfgang Pauli introduced the exclusion principle, explaining how electrons fill atomic shells and why the periodic table exists in its modern form. Their work linked quantum mechanics to chemistry, astrophysics, and material science, unlocking a universal framework that touched every corner of modern technology. A revolution that still isn't finished. By the 1930s, quantum mechanics had evolved into a rigorous science. Yet, its philosophical implications, superposition, entanglement, and the probabilistic nature of reality, continue to challenge our intuition. Today, quantum mechanics drives innovation in computing, cryptography, semiconductor design, medical imaging, and advanced materials. It is not just a scientific theory, it is the operating system of modern technology. If you're ready to dive deeper into how quantum mechanics shapes the technologies we use every day, from microchips to quantum computers, make sure to subscribe and stay tuned for the next video. The future of physics is unfolding right now, and you don't want to miss what comes next.